Hello everybody, and welcome to page 42 in the workbook. And in this page we're going to be working through an illustration that's going to lead us into some of the major theorems about this section 2.1 that we're doing. Okay, so let's read the setup here. So they are saying, suppose that T from V to W is a linear transformation with the dimension of the null space being n and the dimension of the range being m. Okay, so what that means is that we can start by choosing a basis for the null space that has n vectors in it. Okay, so there's a basis for n of t. And we can choose a basis for the range that has m vectors in it. All right, and what we're going to do is to draw kind of a diagram that will let us visually see what it is that we've assumed here and to make some conjectures, okay, about this situation. All right, so down below, we've got our domain and our codomain. Think of T as the mapping that's taking us from one vector space to the other one. And we'll start with the observation that since V and W are vector spaces, we know that both of them contain the zero vector. And from what we've talked about with linear transformations, we know that the zero vector maps to the zero vector. Okay, so that much we can say before we even get started here. All right, what I'd like to do now is to see if we can figure out where these two bases belong in our diagram. So starting with beta n, that's a basis for the null space. And recall that for a vector to be in the null space, it's a vector that's in our domain that maps to the zero vector. So u1 through un would go up here in our domain. And actually, just to save space, let's label those u1, u2, and then we keep going until we get to un. And because those are in the null space, we know that all of those vectors have to map to the zero vector. Okay, so our diagram so far kind of looks like that. Okay, and next, where in our diagram would the vectors in the basis for our range go? Okay, well, they're going to go in our output set, so they're sitting down here in our diagram. Okay. Let me try to be consistent with my colors here, just so this doesn't get too confusing to read. Okay, so W1 through Wm are down here. W2 up through Wm. Okay, and the thing about it is, since those are vectors in the range, we know that they get hit by something. So for W1, for example, we can pick a V1 that maps to it. W2, we can pick a V2 that maps to it, and so on. Okay, Vm and Wm. Okay, and the other thing that we might notice here is that this is just the range. These vectors are in the range, so it's entirely possible that there are some vectors down here in W that don't get hit. Okay, so I'm going to choose to represent those like this. YK. Okay, so by drawing our diagram this way, kind of what we're supposing is that these vectors taken all together form a basis for V, and these vectors taken all together form a basis for W. Okay, that's what we're assuming by drawing this. Okay, maybe one other comment before we go farther here, and that is this diagram might lead you to believe that we're talking about finite sets here. We're really not. V and W are probably infinite sets. We're just drawing vectors in bases in our diagram. Important to keep that in mind as we go through this. Okay, so now that we have this basic pictorial representation, what can we do with it? Okay, well, I'm going to add one other thing to the diagram to help us here. The null space of T you can think of as being that part. Okay, so we'll label that. And now what we're going to do is to make some conjectures, which are going to turn out to be facts that are going to lead us to theorems here. Okay, so first, here's what we could notice about our diagram. The dimension of V we could get by looking at the basis that we circled up here. How many vectors are on that list? Well, notice that there's u1 through un, that's n vectors, and there's v1 through vm, that's m vectors. Okay, if we put those together, that means the dimension of v is m plus n. But what's special about the m and the n? Well, m was the number of vectors in the basis for the range, and n was the number of vectors for the basis in the null space. And so what we get here is the dimension of the range plus the dimension of the null space. Okay, and that's what our diagram suggests. It turns out that this statement is true, and this is a monster theorem in linear algebra. It is called the dimension theorem. Okay, one of the most important theorems in linear algebra. Okay, next, here's another thing that we might notice. Okay, so we also have, where we could ask the question, what would it take for this function to be 1-to-1? Okay, well, if we go back to our diagram, if this is a 1-to-1 function, then it wouldn't be possible to have a bunch of different vectors mapping to this 0 vector in W. What that means then is that these n vectors here would have to disappear from our diagram, because as long as they're there, we don't have a 1-to-1 function. We've got a bunch of different vectors mapping to 0. So what that means then is that n has to be 0. That basis for our null space has to be the empty set. And if n is 0, that just means that the null space contains only the 0 vector. Okay, and what's interesting is it turns out that the converse is also true if you start from this assumption that, oh, and actually that's the 0 vector. Hang on. Let me be careful with my notation here. Okay, so as I was saying, if this works the other way too, if you start from this assumption that the null space is just the 0 vector, you can actually show that that implies that t is 1-to-1. So I'm just going to say it this way. Turns out that the converse is also true. And what we get when we put those facts together is Theorem 2.4, which we'll formally state on the next page. It just says that a linear transformation T is 1-to-1 if and only if the null space contains only the 0 vector. Okay. And finally, one other thing that we'll explore here. We're going to assume, or what if we assume that the dimension of V and W are the same? In other words, that the dimension of the domain and the codomain are the same. Okay, well, let's look back at our diagram here. What would that mean? Well, it would mean that the two bases that we started with, okay, all of these vectors and all of these vectors, there have to be the same number of vectors on those two lists in order for the dimensions to be equal. And since there are the same number of vectors over here as there are over here, that means that these k vectors, okay, have to have the same number of vectors as these n vectors here. I'm sorry, this diagram's getting a little cluttered. So basically what that's saying is that there have to be exactly as many u's as there are y's down here. In other words, n has to equal k. Okay, so k is equal to n, and let's see where that leads us. If we assume that t is 1-to-1, what that means then is, from above we know that that means n equals 0. So if k is equal to n, we have n equals k equals 0. And if n equals k equals 0, what would that mean? Okay, well, if k is equal to 0, that means that these vectors here, y1 through yk, disappear from our diagram. And if those are gone, it would appear that we hit everything. Okay, we don't miss anything down here in our codomain, so that's like saying that t is onto. So far what we've discovered then is that if t is 1-to-1, it appears that t is also onto. What's interesting is it goes the other way too. If t is onto, then as we mentioned above, k is equal to 0. Okay, this list of vectors from here to here have to just disappear. And since we made the observation that k equals n, that means that n also equals 0. And from what we set up here in number 2, if n is 0, that means that t is 1-to-1. Okay, so what have we demonstrated here? What does it appear as true? Well, in the case where the dimension of V and the dimension of W are equal, it appears that T being 1 to 1 implies that it's onto, and conversely, T being onto implies that it's 1 to 1. So 1 to 1 and onto are equivalent in this situation, and that is the statement of theorem 2.5. Okay, now before we conclude this video, I want to just emphasize again, this is just an exploration. Okay, these facts that we've listed, we have not proven them. Okay, we've left a lot of details out here, but it just gives us some maybe geometrical insight into why these theorems are plausible. Okay, in the next video, we'll formally state these theorems and prove one of them.